Hi everyone, the channel Easy Lecture welcomes you. In this video we are going to discuss about log amplifier, and this is a live video. So this is the first time I am going on live. So in this video we are going to discuss about the designing of logarithmic amplifier using PN junction diode, and we are going to discuss the disadvantages of designing with PN junction diode. Due to those disadvantages, we are going to move to an advancement in design, that is designing using BJT, bipolar junction transistor, and then we are going to analyze that. We are going to look after the disadvantages of designing using BJT transistor also, and then here the main disadvantage is the elements which depend on temperatures are involved in the equations. So to eradicate those temperature dependent components, we go for temperature compensated logarithmic amplifier. So these are the things that we are going to discuss, and again we need to know why we go for logarithmic amplifier, what are the advantages, what are the applications of logarithmic amplifier. So those things will be discussed in this video. So before going for further discussion, subscribe my channel Easy Lecture. Now we shall go for further discussion. So here logarithmic amplifier, so it can be used to mix two signals. So usually we have discussed a lot under signals and systems or digital signal processing, that we combine two signals, we multiply one signal with another signal, we perform a lot of mathematical calculations between two signals. In digital signal processing, we perform calculation between one image and another image. So like that it goes on. So here basically we perform mathematical or arithmetic or logic operation between two signals. So here how to perform those signals. So while studying it theoretically, we know that we do it with paper and pen, but in real time application, how does these calculations occur, how does this arithmetic and mathematical calculation and logic operation between various signals occur. So they occur because of the circuit. So to the circuits we provide the input signals, and in the output we are getting the output as the mathematical combination of mathematical operation of various combination of those two signals we get as the output. So here as an example, let us for example, we shall consider that we need to multiply one signal with another signal. Here there is so this is called as mixing of two signals. So here signal 1 is termed as A and signal 2 is termed as B. We need to mix these two signals, that is we are going to perform the product of these two signals, signal A and B. So for that what should we do? First we are sending this signal A to a logarithmic amplifier, and as the output will be getting log A. Similarly we are sending the signal B to another logarithmic amplifier, and there we are getting the output as log B. So we are adding these two signals using a summing circuit, a summer. Okay, so the output will be log A plus log B. So log A plus log B. So it can be written as log of AB, and sending this log of AB to an anti-log amplifier, that anti-log and log they both get cancelled, and finally we will be getting AB, so which is the product of two signals A, B. Okay, so signal 1 is multiplied with signal B, AB. So this kind of mathematical operations can be done very easily using logarithm, using the combination of logarithmic and anti-logarithmic amplifier. In this video we are going to focus only on logarithmic amplifier. So let me illustrate another one example. Okay, so here first we can find even the power of some signals. For example, if we need to find the power of signal A power B, if we need to perform the operation of A power B, so we can do using this illustration. So we are passing the signal A through a logarithmic amplifier, and in the output we are getting log A. Then we are weighting that signal, the output of logarithmic amplifier, we are weighting using a variable, a value B. So weighting means we are multiplying. Okay, so we are multiplying using a multiplier, log A by B. So the output is B times log A. So B times log A can be written as log A power B, and when this log A power B is sent to an anti-log amplifier, as the output will be getting AB. Log and anti-log, they cancel out. So anti-log cancel out the performance performed by logarithmic amplifier. So finally we will be getting only this portion, that is A power B. Okay, so if the value by which we do weightage to log A is 1 by 2, then the output we will be having A power 1 by 2. Okay, which is the square root of the signal A. So this will be highly useful to find the RMS value, root mean square value of signal A. So in this manner, the combination of logarithmic amplifier and anti-logarithmic amplifier are used to perform lot of operations, mathematical and logical operations. So here, so theoretically we know how to perform in signals and systems, or in digital signal processing we do mathematical calculations to do all these operations, but in circuits these kind of circuits are employed or usable to perform these kinds of operations. Now we shall look into the design. So this is a logarithmic amplifier and we have designed it using PN. So it is basically an inverting amplifier. So in inverting amplifier, in the feedback path there is a resistor, and that resistor is replaced by a PN junction diode to perform logarithmic operation. Just see here, in the feedback path a resistor is replaced by a PN junction diode. So all the remaining things are same. Here we are grounding the non-inverting terminal. Okay, so here due to we are giving the input signal to inverting terminal, we need to perform the logarithmic operation for the input voltage, and that should be available at the output. So let us check whether this is happening or not. Okay, so V0, the output voltage should be directly proportional to the logarithmic of input voltage. So let us see whether we are occurring that as the output or not. Here, when signal Vin is given as the input to operational amplifier, the current generated by this Vin is termed as Iin. Okay, so that current Iin passes through this resistor, and after reaching this node there is a chance for it to get divided into two branches, because at this node there are two branches, one into the operational amplifier and another through the feedback path. But what happens, since the input impedance of operational amplifier is very high, it is in the, for an ideal operational amplifier, its characteristics is the input impedance should be infinity, but practically it should be very high. So because of this, the current, it does not enter into operational amplifier. So all the current, whatever the current is generated by Vin, all those current enters into the feedback branch. It doesn't enter into the input of operational amplifier. So whatever the current is generated by Vin, so Iin, all the portions of Iin enter into this branch and it passes through the PN junction diode. So the current passing through the PN junction diode is termed as ID. So obviously what happens, since Iin is passing through the PN junction diode and the current passing through the diode is termed as ID, we come to the conclusion that Iin is equal to ID. Okay, input current is equal to that current passing through the diode. Okay, now we have to derive the equation for diode current. So diode current can be given as ID equal to, the current passing through the diode can be given as ID equal to IS into exponent of VD by if eta Vt minus 1. Okay, so here this Is is the saturation current, otherwise it is called as a reverse saturation current. Then this Vd is the diode voltage. Then this eta is the ideality factor. So ideality factor means the factor by which the practical diode that we are using obeys with the ideal diode. Okay, so the characteristics of practical diode, to what extent it obeys with the characteristics of ideal diode. So ideal diode, the characteristics is, we know, in forward bias, until the voltage is exceeding barrier potential, the current is minimum. Once the voltage exceeds barrier potential, the current increases exponentially. And the reverse bias region, for whatever the voltage increase, there is a small amount of current passing through the diode, that is due to minority carriers. The minority carriers are responsible for the current under reverse bias condition, and when the voltage exceeds a particular value, the junction breaks down, damaging the diode, and that is called as breakdown voltage. So this is the characteristics of an ideal diode. So to what extent this practical diode obeys with the ideal characteristics of an ideal diode. So that is given by this ideality factor. So normally the ideality factor, the value of ideality factor lies in the range between 1 and 2. This is the thing. The next thing, Vt, this is thermal voltage. Vt is thermal voltage. So thermal voltage, it can be given as K into T divided by Q, where K is the Boltzmann constant, T is the temperature, and Q is the charge of the electron. Okay, so here when we compare this portion of equation, this is very large compared to this one. So this equation can be approximated as ID is approximately equal to Is into exponent of Vd divided by eta into Vt, right? And we have already come to the conclusion that I in equal to ID, the input current is equal to the diode current. Okay, so this diode current can be replaced, this equation can be equated to the input current. Okay, so I in equal to Is into exponent of Vd divided by eta into Vt. Now we are going to apply Kirchhoff's current law at this node. So to find the current passing through this resistor, we apply KCL here. Here at this node the voltage is 0. So we already know that at this point the voltage is 0. What is the reason? Because that point is virtually grounded with respect to non-inverting terminal. Non-inverting terminal, so whatever virtually grounded with respect to non-inverting terminal means whatever the voltage that we give to non-inverting terminal, that should occur at that particular point. Here the voltage that is given to non-inverting terminal is 0. That means we are grounding the non-inverting terminal of operational amplifier. So the voltage at that particular node, at that particular point is 0. Okay, so regarding the concept of virtual ground, I have explained a lot while discussing inverting amplifier and non-inverting amplifier. You can refer to those videos to have more understanding on this virtual ground concept, right? Now when we apply Kirchhoff's current law here, we derive I in as V in minus 0 divided by R, that is equal to I in. Okay, so I in equal to V in minus 0 divided by R, that is equal to V in by R. So already we have an equation for I in. Now we are going to equate it to V in divided by R. So from this we can write V in equal to Is divided by R, V in equal to Is into R into exponent of Vd divided by eta into Vt. Okay, again we are taking this Is and R to the left hand side. So when we take it to the left hand side, it comes in the denominator and we get V in divided by Is into R equal to exponent of Vd divided by eta into Vt. Now we have to eradicate this exponent. So what should we do? We have to apply natural logarithm to both the sides, to both left hand side and right hand side. So when we apply natural logarithm to both left hand side and right hand side, what happens? Natural logarithm of V in divided by ISR equal to natural logarithm of exponent of Vd slash eta Vt. Okay, and here natural logarithm and this exponent will get cancelled. Okay, so we have so only this portion of the equation remains. So Vd divided by eta into Vt equal to natural logarithm of V in divided by Is into R. Okay, then we are going to take eta times Vt to the right hand side. So that becomes Vd equal to eta into Vt into natural logarithm of V in divided by Is into R. Okay, so here the output voltage, of this circuit, V0 is same as the output voltage is same as the voltage across the diode, but opposite in phase. There is a phase shift of 180 degree. Okay, so V0 equal to minus Vd. The voltage across the diode is Vd. So V0 equal to the diode voltage is Vd. So V0 equal to minus Vd. So this is the relationship between output voltage and the diode voltage. So already we have derived the diode voltage and we are going to substitute over here. So we can find the output voltage is equal to minus eta into Vt into natural logarithm of V in divided by Is into R. Okay, so from this equation, when we analyze this equation, the output voltage is directly proportional to natural logarithm of input voltage. So from this we can conclude that this circuit is performing logarithmic operation. It is performing logarithmic amplification operation for the input voltage, and then that comes as the output. Okay, now what are the disadvantages of this circuit? We have to analyze that. Here there are certain things involved. This eta is involved, which is an ideality factor, and there are certain temperature dependent components involved, like this thermal voltage and this saturation current. These are temperature dependent components. We have to eradicate this. Okay, so first we are going to focus on ideality factor. We have to eradicate this ideality factor. This ideality factor can be eradicated by designing this circuit by BJT instead of PN junction diode. So we are replacing PN junction diode by BJT, that too in common base configuration. So we shall look at this circuit. So this is that circuit. So in this circuit, instead of PN junction diode, we have BJT, bipolar junction transistor, and that bipolar junction transistor, it is helpful in eradicating that ideality factor. Okay, so here again the circuit performs in the same way. It is also a inverting amplifier circuit. We are giving the input to inverting terminal, and in the feedback path we have a BJT. So the current generated due to this V in is I in. It passes through this resistor, and after reaching this node, entire current passes through the feedback branch. It doesn't enter into the input terminal of operational amplifier, since the input impedance of operational amplifier is very high. Okay, and here that comes as the collector current. Here the current passing through the collector to the collector terminal of BJT, we term it as IC, that is called as collector current. So from this we can conclude that I in and IC, the input current and collector current, they are one and same. Okay, so that is what we have concluded here, I in equal to IC. From the equation of collector current, we have to write the equation of collector current as we did previously, the equation of diode current. Here the equation of collector current, IC, is equal to IS into exponent of VBE divided by VT minus 1. Here there is no dependence on ideality factor. So IS into exponent of VBE divided by VT minus 1. Again this portion, exponent of VBE by VT is very, very large compared to 1. So this equation can be approximated as IC is approximately equal to IS into exponent of VBE divided by VT. So this is VBE, base emitter voltage. Okay, again here talking about this bipolar junction transistor, the base of the transistor is grounded. Okay, and this node is virtually grounded with respect to non-inverting terminal, non-inverting input terminal of operational amplifier. That means the voltage at that node is also 0 volt. That means the voltage at collector is also 0. The voltage at collector is also 0. Here base is grounded, so the voltage at base is also 0. So the voltage that appear here is the voltage between base and emitter. That is the only voltage that appears across BJT. Okay, there is no collector emitter voltage, there is no base voltage. So there is no collector base voltage. So collector base voltage is also 0. Collector emitter base voltage VBE is the only thing that is available. So the collector current IC is approximately equal to IS into exponent of VBE divided by VT. So it is VBE, right? Okay, so a small correction. Right, again we know that IC and IN, the collector current and input current, they are one and same. Therefore we can write IN equal to IS into exponent of VBE divided by VT. Okay, now once again we are going to apply Kirchhoff's current law at this node. Okay, so at this node, due to virtual ground, the voltage at this point is 0. So when we apply KCL, V in minus 0 volt divided by R, that is equal to I in. Okay, so I in equal to V in minus 0 divided by R, that is equal to V in divided by R. Okay, so this I in can be replaced by V in divided by R. So V in equal to, when we take this resistor which is in the denominator to the right hand side, we can write V in equal to IS into R into exponent of VBE divided by VT. And when we take this saturation current, the product of saturation current and resistor to the left hand side, it comes in the denominator, V in divided by IS into R equal to exponent of VBE divided by VT. So now we have to eradicate this exponent, this exponent, we have to eradicate that exponent. So to do that, we have to apply natural logarithm to both left hand side and right hand side without so that does not disturb this equality. Okay, so when we apply a particular mathematical operation to both right hand side and left hand side, the equality will not be disturbed. So here we are going to apply this natural logarithm to both right hand side and left hand side, so that it does not disturb that equality. Okay, so we can write natural logarithm of V in divided by ISR equal to natural logarithm of exponent of VBE by VT. Again, this natural logarithm and the exponent will get cancelled, and in one side of the equation we have only VBE by VT. So VBE by VT is equal to natural logarithm of V in divided by IS into R. Okay, then when we take this thermal voltage to the other side, it comes in the numerator. So we will be having VBE equal to VT into natural logarithm of V in divided by IS into R. Okay, then we have derived the equation for base emitter voltage. Now we have to understand the relationship between output voltage and base emitter voltage. The relationship between output voltage and base emitter voltage is V0 equal to minus VBE. That means the magnitude are same, but they are opposite in sign. There is a phase shift of 180 degree. So V0 can be written as, okay, so comparing these two equations, V0 can be written as minus VT into natural logarithm of V in divided by IS into R. Again, speaking about this equation, in this equation the output voltage is directly proportional to the natural logarithm of input voltage. So we can conclude that this circuit is performing the logarithmic amplification operation, right? Again, when we compare the design using PN junction diode and the design using BJT that so far we have done, the ideality factor which occurred in PN junction diode is completely eradicated in PN junction diode, but the temperature dependent components is still there. This thermal voltage and saturation current, which are temperature dependent components, are still there. Now we have to perform certain operations, we have to change the circuit in order to eradicate this. So this is the disadvantage of this logarithmic amplifier design using BJT. So here we are going for another one advancement in design, that is called as temperature compensated logarithmic amplifier. So here is the circuit of temperature compensated logarithmic amplifier. So here what are the things that we have? Here we are having two logarithmic amplifiers. So one is in the upper portion, to which we are giving the input signal, and we are going to perform the logarithmic operation to this input signal. And in the lower portion we have another one logarithmic amplifier, in that we are giving a reference voltage as the input signal. Then output of these two logarithmic amplifiers are given to a difference amplifier circuit. So this portion of the circuit performs the difference amplification operation. The output of difference amplifier is given to non-inverting amplifier circuit. It is given to non-inverting amplifier circuit, right? So what are the things that are happening here? Let us see. Here this V1 is the logarithmic amplified version of Vin. Okay, so whereas V2 is directly proportional to the natural logarithm of this reference voltage. Okay, and then V1 and V2 we are giving V1 and V2 as inputs to this difference amplifier circuit. V2 is given to non-inverting terminal and V1 is given as input to inverting terminal. So the output voltage V0 equal to V2 minus V1. Now let us go for mathematical calculation. So V1, it is directly proportional to the natural logarithm of input voltage Vin. Okay, so V1 equal to minus Vt into natural logarithm of Vin divided by Is into R1, where Vt is the thermal voltage, Is is the saturation current, R1 is the resistor which is used in the input side. Okay, similarly for amplifier V2 is equal to minus V2 into natural logarithm of V reference divided by Is into R1. Since the reference voltage is used as the input for the lower logarithmic amplifier, we are arriving at this equation. Okay, and then we are going to send this V1 and V2 and this minus V2 into natural logarithm of Vin into Is into R1. So this minus into this minus becomes plus, right? So we are getting this equation, minus Vt into natural logarithm of V reference divided by Is into R1 plus Vt. So Vt is common. When we take Vt common outside, we can write this equation as natural logarithm of Vin divided by Is into R1 minus natural logarithm of V reference divided by Is into R1. So that can be written as by Is into R1, it can be written as Is into R1 divided by V reference. So the minus sign which was here can be cancelled, right? So Vt into natural logarithm of Is into R1 divided by V reference into Vin divided by Is into R1. So this Is into R1 and this Is into R1 are cancelling out each other. So finally we are getting V0 as the output of difference amplifier as difference amplifier as Vt into natural logarithm of Vin divided by V reference. Okay, again, what are we doing in the temperature compensated logarithmic amplifier circuit? We are passing this V0 voltage to non-inverting amplifier circuit. Okay, and that is the final, the output of this non-inverting amplifier circuit is considered as the final output. Okay, temperature compensated output of logarithmic amplifier. So we are passing through this passing this V0 output voltage of a difference amplifier to non-inverting amplifier circuit. So what is the output of non-inverting amplifier is 1 plus Rf divided by R1 into input voltage Vin. Okay, so here comparing this one over here, Rf is the feedback resistor, R1 is the input resistor, Vin is the input voltage that we are having. So comparing this equation with the circuit that we have designed, Rf is R2, then R1 is RTC, then Vin is nothing but the output of difference amplifier. Okay, now we shall write this equation as here. So the output of non-inverting amplifier VO comp, the compensated output of logarithmic amplifier, the final output is 1 plus Rf by R1 can be written as 1 plus R2 by RTC into V0. V0 is the input voltage to non-inverting amplifier, but it is the output voltage of difference amplifier. So the value of V0 we have derived already. It is Vt into natural logarithm of Vin divided by V reference. So we are substituting this. Okay, so finally the temperature compensated out. Conclusion that the temperature dependent component is eradicated here? No, because the saturation current, one of the temperature dependent components, is eradicated. Is the saturation current is not there, so it is missing. So we have cancelled out it, but still voltage is there. Okay, the temperature dependence of the circuit is there in the form of thermal voltage, the dependence of this circuit with respect to thermal voltage. So that can be eradicated by using this circuit. So I forgot to speak about this resistor RTC. It is the temperature dependent resistor. It is otherwise called as sensistor. Okay, so the resistance of this temperature dependent resistor in such a manner that it cancels out the effect produced by the thermal voltage. Okay, so here the RTC that we are using as the input in the non-inverting portion dependent components of logarithmic amplifier.